So let's see how it works. Okay, so I'm going to talk about soil salinization and acidification. And I start with this slide, just saying that we care about this because it impacts people all around the globe. About 1.5 billion people live in soils, in lands that are too salty to be fertile. And usually these people live in developing countries. Here's a map of the global extent of salinization and acidification. And we see that it is present in all continents, but mostly in arid and semi-arid areas. And usually those same areas are where we have developing countries, but not only. Famously, Australia is well impacted by salinization and acidification. But we see that in Northern Africa, the Middle East, Central Asia, we have great extents of land impacted by salinization. Salinization can have many causes. Most simply, we see in this picture that whenever we bring water to a field by irrigating, this water has some concentration of salts in it, and the water evaporates, and water is uptaken by plants, and eventually there's transpiration, and the salt can accumulate if there's not enough drainage of the salt. And this can happen when we are in a arid or semi-arid area where we have not a lot of water to irrigate with, and not a lot of rain to wash the soil from the salts. In this similar picture, we see a few more effects. Salinization can be caused by salt in the groundwater. If the groundwater water table is high, so it can bring salt to the field. It can come as because of contact with seawater. And I talked about irrigation, and there's also the topic of changing climatic regime of rainfall, and that can greatly change what happens to the accumulation of salt and sodium, particularly in the soil. And here we are in a Mediterranean country, and we have well-defined seasons, and we depend on the wet season to wash the salts from the soil. So what happens when climate starts changing, both in shorter, for example, shorter wet season, or more extreme events? And those are interesting questions to me. Here in those yellow circles, we see cations. So salt can be many things. We can talk about cations and anions, and in this talk we will focus mainly on two main cations, sodium and calcium. The main question that will guide my talk today is whether soil salinity and acidicity can be irreversible, because this problem affects so many lands around the globe. If it is the case that salinity, and particularly acidicity, is an irreversible problem, then every year more and more land are leaving they're not being productive anymore. And of course, this is a problem for a world with increasing population and increasing food demands. So, and the short answer is that yes, it can be irreversible. And the question of irreversibility is the main question that I would like to talk about today. So first, I would like to acknowledge my colleagues in research. Foremost, my students. They are here on the left of the screen, and we, in the past years, we've published a few papers on this topic, and I'm taking graphs and main conclusions from all those projects that we have had during the past few years. From the Volcanic Center, I have Guy Levy as a colleague helping us with the experimental part. And I'll talk about the experiments we've made, and Nadav Peleg as our climate expert. So here I have a video, my student made this. So we have soil aggregates and water can flow in between the cracks through the pores. And whenever we bring salt to the soil, and particularly sodium, it greatly changes the physical properties of the soil. Those aggregates can, first, they can swell, and the clay in the aggregates can disperse. So there can be a change in this physical soil properties. And because of that, we expect to have changes in the flow of water through the soil, because the pore system will greatly change because of particularly sodium. So this is in a nutshell the main problem that I will be talking about. So a few definitions here. I will be talking about salinity and sodicity, and salinity can be defined in many ways: the electrical conductivity of the water, of the soil water, or total dissolved solids. But here, when I talk about salinity, I'm talking about the concentration, the electrolyte concentration of soil water, and it is just the amount of cations we have in the soil water. When I'm talking about the sodicity, there are two main ways of describing sodicity. One is the sodium absorption ratio, and it's used for water to qualify how sodic is a given water. But in this talk, when I refer to sodicity, I'm talking about the exchangeable sodium percentage. So those brackets, they denote the cations in the exchange complex. They are adsorbed to the soil particles, and the ratio, the relative proportion of sodium in the exchange complex in the soil particles, this is the exchangeable soil percentage. Okay, so so if we translate that video, that animation into a graph. So I took this graph from now an old paper, and we have on the horizontal axis the concentration of salt in the water, and in the vertical direction we have the hydraulic conductivity, the velocity by which water can flow through the soil. And we have many curves here. Each curve is an experiment done with different sodicity level. So say if we take this sodicity level and we start here and with the higher concentration, and we decrease the concentration of the water, then we'll expect a reduction in hydraulic conductivity. And it depends on the concentration. It can be really low and really shut down the flow through the soil. And of course, this is more pronounced the higher the sodicity. So here we see, I don't know if it might be too small for you to see. This is SAR 50, a very high sodicity level. And for lower sodicity levels, we have different curves. So we have different degrees of degradation in hydraulic conductivity. So also when I talk in this talk about soil degradation, I'm focusing specifically on the degradation in hydraulic conductivity as a proxy for all the effects that salt and sodium particularly cause in the soil. So this is a classic graph, and many other experiments like this have been conducted in the past decades, but they have also they have one thing in common, is that they only measured the degree of degradation. They start with a high concentration, and slowly they reduce concentration, and it goes in this direction. So we see this red arrow. It's always from the right to the left. And I got interested in this topic during my postdoc, and I was looking for papers that described, okay, now that the soil is degraded, what will happen if we go back and we increase the concentration again? So how will the soil be able to rehabilitate? Will we see a high rehabilitation? Will hydraulic conductivity go back? It might not go back to the same levels as it was before, and I just couldn't find it. So when I came here to the faculty, one of my students, he made this soil column experiments to test exactly that. So here we see soil columns, and we have water of different salinity and sodicity flowing through those soil columns, and we measured the flow of the effluent, and we did that for various kinds of types of soil with varying degrees of clay. Clay particularly will be sensitive to sodium, sensitive to swelling and dispersion for higher sodicity levels. So that's what we did, and this is one graph. I'll talk in some detail about this, and I'll later show a lot of other graphs that we measured. So here are the same axes as the old graph from before. We have salt concentration in horizontal axis and the relative hydraulic conductivity. It's relative because we normalized. This is 100%. So here we have the black curve, and it goes down. So we start here from the right, top right, and we decrease concentration. And as expected, we find that the hydraulic conductivity goes way down. What we did is that we see these black dots here. We stop in various points in the middle, and we go back to the previous concentration. So we have those colored curves. So we call them first order reversal curves. So they are reversal curves because we reverse the trend. Instead of decreasing the concentration, we make it go back up. So it depends on the degree of degradation. If we stop here and go back to the right, so we have the orange or the purple curves. The purple starts here, and it can go back. It can backtrack exactly the degradation curve. So no irreversible damage was done to the soil. When we came back to higher concentrations, then we achieved 100% conductivity as before, and that's great. But it depends on the degree of degradation. We can get lower degrees of reversibility. Here we see something like 90%, and the blue starts here, then it goes to something like 75% or 70%, 60%. So really, it depends on the degradation, on the degree of degradation. We will see that the soil will not rehabilitate 100%, and it will not go back. It will stay at these lower levels. So, and this we will call irreversible degradation. I use the word irreversible in the same sense that I use the word hysteresis. Here we see a hysteresis graph. A hysteresis graph is a graph where the way in and the way out are two different paths. So when I talk about irreversibility or hysteresis, this is what I mean. So this was for one particular soil, for one particular sodicity level. We vary the salt concentration while keeping the sodicity, the SAR, constant. But of course we can do that. So here we see that for, say, SAR level 10, which is already high, and we do these hysteresis curves for those three soils, and we can change the SAR 20 and for the same soils. And so we produce lots and lots of hysteresis graphs for all the soil types we conducted the experiment for. and for many sodicity levels, so up to 50, which is super high. But we wanted to test the system and see what happens. I would like to focus here on one particular aspect. So let's focus on this graph. So we start here on the top right with very high concentration, and we decrease the concentration, and relative hydraulic conductivity goes down. So if we stop here at concentration 20, and then we reverse the trend, then we find that here, I don't know, this is something like 80% hydraulic conductivity with respect to the initial one. But if instead of stopping at concentration 20, we decrease it a little bit more to 15, then, and only then we reverse, we see that the path to the right is quite different. We don't go back to, I don't know, 75% or 80%. It stays flat, horizontal at 60%, right? So we see that very small changes in the degree of degradation, they can have a very large impact in the outcome in the future history of the soil. So, and that takes me to my first take-home message of the talk, which is that irreversible soil degradation is real, it is quantifiable and possibly extensive, and that small differences in degradation can have far-reaching consequences. So that was the experiment we made. Now we wanted to make to play with this. So it is very time demanding doing those experiments. Every single point here, it is 3 different columns. We did 3 replicates, and we wait a very long time for flow to stabilize in terms of the flow and of the chemistry of the water that goes in and goes out. It takes weeks and months for to produce those graphs, and it is very time demanding. And we did that for only 3 soils. So we wanted to learn from those experiments and start modeling soils in general from those 3 representative soils, how we can make sense of how soils in general will respond to salinity and sodicity. So this is the only graph that I will have about the mathematical framework. I find it quite challenging to convey those ideas, especially through a Zoom talk. And to this day, my student and I, we studied that for many months and years, and it's still kind of confusing to me. So I don't think I can convey that in a few minutes. What I want to say that this is the same graph, experimental graph we had before, and with some mathematics that I don't show to you now because I don't think it is worth it. There is a mathematical framework. We did not invent it, we adapted it. It comes from physics, from the physics of magnetism, where we famously, there is the effect of hysteresis. There is a mathematical framework that can help us understand this kind of hysteresis we see. So this whole mathematical framework hinges on us producing weight functions, which are those colorful triangles. This is a weight triangle. And with that, we can model, and this weight triangle, it will completely describe the behavior of this soil to changes in salinity and sodicity. So if we model that, and this is the weight triangle we produced, then if we play with it, what will the model produce? So those colored curves, they are supposed to depict the same experimental curves we see. And it is up to up to a point, we think that they describe well enough what's going on. So then we can start playing with weight functions and start talking about what will be the weight function of a clay soil or a sandy soil based on the experience we had with the experiment. And with this mathematical framework, we can start producing a language to talk about degrees of degradation and degrees of rehabilitation of the soil. So we developed two indices, the degradation index and the reversibility index. And based on those points and those two graphs, they show how the three different soils, sandy loam, sandy clay loam, and clay, so those three different colors, how its degradation index and reversibility index vary as we vary the sodicity of the water. And in both those graphs, the degradation index goes up as the likelihood of degradation goes up. And the reversibility index goes up as the likelihood of rehabilitation goes up. What we can learn from this graph, what I learned from this graph is that, let's take the black curve. The black curve, it is the clay soil and is the highest curve here. So as expected, this is not new. It has been measured a lot of times before. As expected, the clay soil is more prone to degradation, to swelling and to dispersion, and that was expected. And as the amount of clay in the soil goes down, then the likelihood of degradation also goes down. And the likelihood of degradation goes up with SAR. So the top graph is completely expected, and this is not new. The bottom graph, it is indeed new because it was never measured. And we could quantify not only with what's the likelihood of a given soil to suffer degradation, but with what ease we can make it go back to its original state. So that's what the reversibility index measures. And now we see that there's not a one-to-one correspondence between the likelihood of degradation and the likelihood of rehabilitation. So let's say the red curve here, it is the sandy loam. It is the soil with the least amount of clay. So it is the least likely to suffer degradation. But for this given SAR value, for this given sodicity level, it is the one, and it is also the one that it's more, it is also the one that it's easiest to rehabilitate. So it is hard to make it degrade and easy to make it go back. The black one, it is easier to make it degrade, to make the hydraulic conductivity go down. And it is hard to make it go back up. Now, what's interesting is that the order red, blue, and black is not conserved here in this bottom graph. So we see that the black and the blue, they reverse. So the blue one, it is harder to make it rehabilitate, but also harder to make it go back to its original state. And that takes me to my second take-home message, which is that the susceptibility to degradation and the propensity of rehabilitation are independent. We cannot naively say that, oh, if I have a given soil and if it's easy to degrade it, then it must be hard to rehabilitate it. Or if it's or the other way around. We cannot say that. For different soils, we have those two different characteristics, and they can not correlate necessarily. So they are independent things, and this is something new we learned from the experiments and from modeling the hysteresis graphs with the proper mathematics. Okay, so going forward, for a few years now, we've been developing this model we called Salt of the Earth. So the acronym would be SOT, and in Hebrew, if you are tempted to read Soteh, it doesn't sound good, so we say it's SOT. But it's Salt of the Earth. And in very general terms, it is a model that describes the dynamics of soil water content, theta, of soil water concentration, C. And so this is water, salinity, and the third is sodicity, the exchangeable sodium percentage, ESP. So we can simulate the dynamics of a given soil, of a given depth, of a given texture, how it will be affected by irrigation, by rainfall, and all sorts of effects. The main features of this model we developed is that there is an exchange reaction, and we only assume sodium and calcium cations. So it's not the most general model ever. It is if you are familiar with other models such as Hydra's, and Hydra does everything. So our model does very few things. We did not want to make it too complex. So we have only sodium and calcium cations. And the main feedback in this model is the feedback of the saturated hydraulic conductivity, Ksat. And Ksat, the hydraulic conductivity, is dependent on the concentration of the soil water and on the sodicity of the soil. And how does it depend? Well, we use the same mathematical framework that we developed before to understand hysteresis. So this function here, it's not a simple function that given a value for concentration and sodicity, we get immediately the hydraulic conductivity. It is history dependent. It has memory. So the whole history of the soil will affect its current state. And that's the main feedback of this model. And as I said before, we can have irrigation water of any quality that we choose with any electric conductivity and SAR. And we can play with rainfall regimes in any way that we want. So now I'm going to show a few results of this. Here you see graphs that show time here in the horizontal axis in years. And in the vertical axis in each of those panels, we have the relative hydraulic conductivity. So we track how hydraulic conductivity changes in time. We see that we have those thick curves and those thin curves. So we did stochastic simulations with a very large ensemble of, I don't know, many thousands of simulations. Every simulation has a different rainfall pattern. So we see that the blue shaded area is the rainfall season, and the white is the dry season where we have irrigation. And here in the rainfall season, we have, for every realization of the simulations, we have different stochastic rainfall. And the thick curve is the ensemble mean. So we average over all these runs to get the average hydraulic conductivity. And every panel here has a different soil. We see weight function A1, A2, B1, B2. So we model different kinds of soils that are more or less prone to degradation and to rehabilitation. So if we have those two axes, degradation and rehabilitation, so we sample soils from all options to see how they will respond over time to a particular irrigation water quality. And it has a high SAR value, a high sodicity level. So we see that some soils, those A1 and A2 soils, they would be less prone to degradation, and we stay at 100% all the time almost. But those green curves, they start to go down. This one, at the beginning of the irrigation, it goes back up. It happens that during the rainfall season, the soil water is more diluted, and diluted water causes hydraulic conductivity to go down. So that's where we see degradation. And usually when it goes back up, it's when we irrigate and we bring soil to the field. So here we see that over 2.5 years, we see some reduction in the average hydraulic conductivity. And if we increase even more the amount of clay in the soil, so those C1 and C2 soils, they are much more prone to degradation. And here we see that we have irreversible degradation on average. It depends on the soil properties. So what's the difference between the C1 and C2 soils? They have exactly the same likelihood of degradation. So you see that those curves going down, they are the same. But when, when the irrigation season, the dry season starts, this one is much easier to rehabilitate, and this is much harder to rehabilitate. So we played with that, and we saw how different soils might react over the long run. This last graph here, I find it important because McNeil is the same researcher that I showed the first graph from the 1966. It's from him. And this McNeil function, he published in, I think, in another paper from 1968, a function of how to describe the change in hydraulic conductivity as a function of salinity and sodicity. Now, what this function has is it is memoryless. Unlike our mathematical framework, it has no sense of what was the past state. It only cares about what happens right now. And this is what all models that we are aware of, this is what all of them do. They have no memory, they have no hysteresis effects. And here we see, I'm not sure in my screen I can see it clearly, that there are some thin curves that when there's degradation, it goes way down. And also see the scale here, it goes from 0% to 100%, while all other graphs were from 80% to 100. So those changes in hydraulic conductivity, they are much more abrupt here. It can go instantaneously down and then instantaneously up. You see, as we start irrigation, they all go up and that's it. So this is the present state of most models around, where they don't take into consideration any hysteresis effects. It's like whenever someone uses any kind of description like the McNeil function, and there are other kinds of descriptions, implicitly we are saying that there's no irreversible effects going on. We can play with our model. Right now we are, in a few minutes, I'm going to talk about what will come next. Here you see SOAT 1.0. This is SOAT 2.0. That's the latest version. In the older version, we still did not have this this hydraulic conductivity feedback. So the first version of our model, it used exactly this McNeil function, or one very similar to that, where we did not have irreversible effects. And what we're doing is right now we are integrating, but we still can't, our model is amenable to this kind of investigation. So we can, what can we do with it? We can choose very different irrigation water qualities and see what will be the effects on the dynamics of soil moisture, concentration, so this salinity, sodicity, and relative hydraulic conductivity. Another thing we can do is play with the weather. So here we have 2 rainy seasons with 2 shades of blue. Right now, I think this was for the northern Negev region. We have a rainy season of approximately 130 days. But there are models that they predict that in the coming decades, the rainy season here in Israel will get shorter, and it could get shorter up to 80 days or down to 80 days. So how would different rainy seasons affect the accumulation of salt, of sodium, and particularly what it will do to the hydraulic conductivity. And last, I have here 3 different soils and how they respond to cycles of drying and wetting. What I find interesting in this graph is the following. We have 3 different soils with increasing amounts of clay, like 6%, 16%, and 48%. So we did measure soils more or less like this, and we saw that consistently, those soils that have more clay, they are more prone to degradation. But what do we see here? So this last panel, we see that we have the relative hydraulic conductivity. So those thick lines, they're only the averages. But if we have all the simulations, and after 4 years of simulations, we do a histogram of what happened to the hydraulic conductivity. We see that for the red and the yellow, so red is the one with the least clay and the yellow is with the most clay, they all have 100% hydraulic conductivity, and the black one, the one with the intermediate amount of clay, this has a reduction in hydraulic conductivity, actual reduction in hydraulic conductivity. So what I learned from this is that although it is true that in general, clay soils, they are more prone to degradation, we cannot say that the risk for degradation is higher for clay soils. What I learned from this last panel is that the actual risk of degradation was higher for this clay, for the one with this intermediate amount of clay. So we decouple the concept of propensity to degradation with actual risk. In order for us to talk about actual risks, we have to talk about the likelihood of rehabilitation, which I talked about before, and also run simulations that have a time component, like this SOLT, the SOLT model does. So, and the third take-home message is that actual degradation risk, it is different from susceptibility to degradation, where susceptibility to degradation correlates with the percentage of clay of a soil. I think I'm reaching the end of my talk. Those are the three take-home messages that I talked about. The first was that small differences in degradation can have far-reaching consequences. The second was that susceptibility to degradation and propensity of rehabilitation are independent things. And the last one was that actual degradation risk is different from susceptibility to degradation. What we want to do in the very near future, we are preparing another paper which does similar things from what I showed you in the last graphs, but not with SOLT 1.0, with the latest version, which does take into account the hysteresis in hydraulics conductivity. So we will be examining how changes in climate will affect degradation in one specific area in California, which is a very productive area in terms of agriculture, but it does suffer from salinization. And this is the end of my talk. Thank you for listening, and I will be glad to answer any questions.
Thanks, Yair. Any questions?
I have a question, Yair, if possible. Hello?
Yes, I hear you.
Okay, thank you very much for your talk. Very interesting. I just wanted to ask, to my knowledge, typically when talking about hysteretic phenomena like in magnetization or applying some general models, old models like Preissach model, they are talking about kind of transition, kind of the transition which happens, which means there's some intrinsic process like transition which is involving hysteresis. So if it's magnetization, it is orientation of magnetic dipoles and in one direction. If it is a condensation in pores, so there is some intrinsic property like condensation and emptifying, which is maybe not clear by itself, but that's the reason then there is a conception how to summarize it using some distribution function. So what is the physical-chemical basic mechanisms, if it is relevant for you, of course.
Mhm.
What is the chemical mechanism which should be responsible for this basic hysteretic response? What is
Yes.
element? What is the elemental hysteron? Why does it happen?
Yes. Thank you. So you mentioned the Preissach model, and that was exactly the mathematical framework that we used. We adapted it to our needs. So we did use the Preissach model. So indeed, in every context, we can define what is the basic component, the hysteron, that goes on and off. And we did not do that for us, for our case. I am not an expert in those areas, and this would be a research more oriented to the micro processes in the soil aggregates, in the clay platelets. So we used the Preissach model because it could conveniently, it could describe the kind of hysteresis curves that we did measure. But we did not hypothesize what's going on in the micro level. We do when we use the Preissach model to explain our data. I think implicitly we talk about the fact that we have heterogeneity in the response of different aggregates to salinity and sodicity. So if everyone responded exactly the same way, we would not have we would have a step hysteresis, like a very sharp, and we don't have that. We have smooth curves. And I think this is the result that different parts of the soil, they respond very differently at very different points to degradation and to rehabilitation. But what's going on in the micro level, that I don't know.
Okay, and I have one more probably specific question. So if I understood right, so there is no straightforward relation between clay content and degradability. That's what you said in the end. So my question
Of
is,
risk.
yeah, but my question is, it maybe I don't know what kind of the soils did you work. There's a role of organic matter, which is not necessarily correlates with presence of clay, which organic matter may affect on dispersion of clays, and then might be some complicated phenomena which might make a prediction not so straightforward based only on clay content.
Absolutely. Absolutely. Both our experiments and our modeling approaches, they are minimalist. We try to push aside all kinds of complicating factors like what you mentioned, such as organic matter. So of course, soil is complex. And this was a first attempt to describe the phenomenon I talked about. Right now, I wouldn't know how to incorporate organic matter into the mix and see. I think it, sure, yes. So the answer is yeah. One should take that into account. We haven't, because it was a first attempt to try to describe this phenomenon. And yeah, of course, we didn't take other factors into account. We didn't take the mineralogy of the clay into account. We didn't take I don't know, lots of things. Should what I wish to what I would love to happen is that other researchers got interested in those questions and they helped me think about this and also to measure those. I can cite, I don't know, many papers that described the phenomenon just in the degradation part. And from all I know, the paper that we are about to get published in Geoderma is the first that goes back. so it is very data poor, this whole subject.
Thank you. Thank you very much. Thank you.
Hi, Yair.
Hello.
I have a small question. Did you measure or test the option of changing the reducing the SAR of the or the ESP of the soil? What this cause? If it's
Yeah.
the reversibility?
Yeah, so there are two things. Yes, thank you. In all the experiments that I showed you, we fixed SAR and we go back and forth in concentration. And yes, we should do the other way around. We should fix the concentration and go up and down with the SAR. For sure, that was not something we did here in our lab, but I am collaborating with a colleague from Australia, and he's doing exactly that, both what we did and the other step with Australian soils. And this is something we absolutely need to characterize the soil with the mathematical framework of Preissach and stuff. Yeah, we need to approach from both sides to fully characterize, yes. But it is so time consuming. Yes, it's amazing, especially, of course, when the pores are clogged, nothing moves. It's horrible. Yeah.
Udi, can I ask?
Yeah.
Hi, Yair.
Hello.
Daddy Russo has a model that describe or can predict the hydraulic conductivity given changes in C and ESP, like you have done. And he has also their threshold value where the degradation is irreversible.
Mm-hmm.
Have you looked at the correspondence between the two? If your point also of irreversibility correspond to his predictions? Because his model is more at the level of the clay platelets and what's happening there.
Mm-hmm. Yeah, so he gave a talk here in our department, I don't know, a couple of years ago before the pandemic. And I asked him exactly what the connection between what I'm studying and what he does. And I remember that. And so what he did is his way of not letting there is some component of irreversibility in his model for sure. It's just that it is just like lowering the ceiling and not letting the curve go back up. It's just like a hard lowering of the ceiling, and now the curve can go back down. We kind of did that with the results I showed in SOLT 1.0. Some of the results, we did not still have the effects of hysteresis, but we so badly wanted to see what it does. So we did a similar approach to what Daddy Russo does, that whenever we like him, like well, it's not casual, it's not by chance, because we communicated. We defined a threshold, like, I don't know, 80, 20% reduction or some threshold, and beyond this 20% reduction, then whenever the curve goes down, then it cannot go back up. It's very similar. So we have not explicitly compared our results from to his models. They belong in the same family. What I can say is that we took this one step forward, and we can very finely define not one boundary between nothing happens and okay, there's irreversible degradation. It's a smooth, you can go back and forth. You have this whole richness of hysteresis curves, and you can do whatever you want. I think so. We go in this direction, but in my mind, we go a little bit forward. Although we don't talk about the physics and chemistry of the micro processes. We absolutely do not.
Any more questions before we finish? Okay, so if no more question, then I would like to thank you again, Yair. It was a very nice seminar.
Thank you. Thanks for
coming.
inviting, and I'll see you around.
We'll see you. Yeah. Thanks, everyone.